So I'm happy to talk to you today about this report by the National Academies that I had the honor of chairing together with the Vice Chair, Bobby Alal, who is an innovation scholar. And you're going to understand why I'm saying that once I get into the report. It's on Achieving Science with CubeSats, Thinking Inside the Box. That's the title we chose. And you know how the National Academy works. First of all, I did not put this committee together. The National Academy did it based on balancing conflicts and also covering the breadth and depth of what's there. You look at this list and you see people who are CubeSat experts. You know, people like Tom Woods has done CubeSats for a number of times. He's in fact a PI of an active mission right now. You see Julie from JPL, who's also a CubeSat expert. Then you see people from new space like Andy Clegg, works at Google and a variety of missions there. And then Tom Young, some people would lovingly refer to from old space, right? The kind of the Lockheed Martin, kind of a really disciplined thinker, an amazingly valuable member of the committee, but a person when we started, I think, who was super critical about CubeSats, as were, I would say, close to 50% of the people there. You see also that there's science disciplines that are covered both from solar and space physics. You see Robin Millen there, many of you know. You see, of course, earth sciences, Bill Schwartz, and so forth. You know, so kind of disciplines in that way, but also some technology experts, such as Paolo and Malcolm, who are technology experts and have done a lot of work, as did Charles Norton, who's in charge of the JPL CubeSat efforts. So I want to tell you about this report and also the consensus recommendations and conclusions that came from it. And I want to tell you, if I put those on the table on day one, we would have not been able to agree. And the major reason is just because of the diversity of the group. We wouldn't agree because people come from different perspectives. So basically what I'm going to tell you is both what the underlying data are that made us agree, and then basically tell you that every single thing that I'm going to tell you about, the conclusions and the recommendations in there, are unanimously agreed upon in the entire committee. So that's where we got. Why did NASA and the National Science Foundation ask for this report? And it really did because CubeSats are getting a lot of attention. You see on the left, Aviation Week, one of our key trade magazines that has CubeSats on it. On the right, you see Science magazine, which really got people's attention because you know, people would have understood why some technologists were interested in CubeSats, but perhaps initially not, why scientists were interested in CubeSats. And so basically because of that and the various investments that happened, NASA and the NSF asked the National Academies to really look at this. They, like everywhere in the Academy, they gave us a specific charge. We responded to that charge and nothing else. That's going to be really important when we talk about policy, for example. We would have liked to perhaps add here and there recommendations and so forth, and we didn't, because that's not part of our charge. The charge was really simple and threefold: to develop a summary of status, capability, availability, and accomplishments in the various sectors from CubeSats, and then recommend potential near-term investments that could be made to improve these capabilities and the usefulness of CubeSats. And finally, to identify a set of sample priority science goals that describe near-term science opportunities. It's really important to understand that last point right. So our goal is not to prioritize all the science that happens in CubeSats. We did not have enough depth on the committee, I just showed you. You need more people to do that, just more perspectives. But what we try to do is really show sample priority science goals that kind of indicate where the directions are in which CubeSats are the right tool. And so kind of bottom line up front, this is what I'm going to talk to you about. First of all, I'm going to convince you that this report is really based on the most detailed analysis of the available data right now. The data are moving really rapidly, I'm going to show you. And so basically all the data are effective end of last year. So December 31st of 2015. That's where we made a cutoff. We recognize, based on these data and the analysis thereof, the similarity to disruptive innovation. I'm going to explain to you what that is and why that is relevant. And then in accordance with the charge, did an analysis of science publications and in fact conclude that CubeSats not only can do high priority science, they already have. And so I'm going to tell you what we did to achieve to that conclusion. But then also we recognize that there's science potential in all science divisions to varying degrees. However, not every application is appropriate for CubeSats. Not surprising, but that's what the second sentence is about. The first sentence may be surprising, frankly. Certainly is not a sentence that, again, we would have agreed upon in meeting number 1. And then the final point is that this potential can only be materialized if a number of conditions are fulfilled. And the conditions are related to technology and industrial connections. They're related to policy issues and related to programmatic and management issues and the inside of the agencies. So that's what I'm going to tell you about. So I'm going to step through it and use as a first slide what is a CubeSat. It's a funny story. I gave this talk at the National Science Foundation. I got through it, and the first question is, what is a CubeSat? So I never make that mistake again. So a CubeSat, for the purpose of this study, is defined as a spacecraft sized in units of U, 10 centimeters on edge, kind of a liter in volume, typically up to 12 U that is launched fully enclosed in a container. If we ask this definition 5 years ago, it would be a different definition. You probably wouldn't have gone to 12U. If we asked it in 5 years, God knows what we'll do. So we actually stayed away from creating this kind of definition overall and really define it for the report. So you know how we define it. So the report is reproducible in some ways, right? So that's what we define it as. This is one of the pictures that that will help you understand what this is. You see a primary payload at the top. This is a payload being integrated, a main payload, and then a CubeSat in a canister at the bottom that is being assembled here. And so kind of the CubeSat is small compared to the big payload, and in many payloads even smaller, kind of as a ratio than this one. So this is kind of the image you should have in mind. So to talk to you about CubeSat, one way to do this is to reach back and really look about the history. And I'm sure I invite others, in the discussion session and give their own spin on history. What we try to do is really show, as a function of time here, the US CubeSats launched by mission type. Note that only the CubeSats in the public domain are shown here. There's a whole number of CubeSats that are not in the public domain, which we did not have access to, and they're not shown here for that reason. The whole CubeSat story started early on, but really as CubeSats, basically as a word, CubeSat started in 1999, basically when 2 professors, one from Stanford, one from Cal Poly, came together and really thought about the educational opportunities to aerospace engineering students. I mean, largely speaking, the problem that many engineering fields face, especially aerospace, is that payloads are super expensive, super slow, big, and you need to be certified to work on it. Therefore, many of our students that we educate in aerospace engineering do never have the opportunity to actually touch a payload. I have touched a payload that's in space during my education, and I'm one of very few who did that before CubeSats. And so basically what these 2 professors did is they really came up with the idea of both creating that standard, but just equally importantly, the innovation really is to develop that container that really is used to be launched. And there's a history to that. This is not the first time they ever thought about. The Air Force did some interesting things. There's other things that happened there. But the point is that my computer wants to upgrade. The point is that this really was at the beginning of it. Very early on, the vast majority of opportunities that people were looking at, therefore, were in the realm of education, kind of crossing into technology. Now you see that education in yellow and then technology, science in red, which is what I'm going to ultimately talk about. You basically see that there's not many launches early on. Why is that? Well, it was really hard for these colleagues to, in fact, convince the launch providers to give them rights. And so you see that early on there are some launches in different colors, and that is because Ames jumped on board right away. And Pete Warden, a Michigan grad, was at Ames there, and I always describe him as a 3 sigma guy, right? He was kind of out there ahead or in front of people, and got people working on CubeSats within Ames, and so basically what you see is education is really the dominant thing that's happening, dominant investment. The DoD started investing in this technology kind of in the mid-2000s or even early 2000s, and really the technology inventory that we're benefiting from in many cases relates to kind of a heritage that comes from the DoD investments. But what you really see on the DoD, there's an investment that went up, and then there was this kind of damning DoD report, that basically an Air Force report that basically said that small sats are really not useful for the strategic needs of the Air Force, and so the investment kind of went down again. There was, however, a really important development in the National Science Foundation. Therese Jurgensen and Rich Benke created, recognized that these CubeSats are being built there, and basically reached out to you, Jamie, and some others within the field, and really got convinced that it is possible for the National Science Foundation to develop these payloads at a cost that's comparable to what normally the NSF does, which is of the order $1 million if you look at kind of investments, that it's possible to do that. And they created a workshop in 2007. I have to tell you, I was in that workshop, and I only went because Rich twisted my arm, to be frank, because I did not believe, I'll be very frank, that these CubeSats ever amount to anything relative to science. Based on my experience building instruments, I thought there's a certain volume that you need, but I felt that the educational kind of narrative was really important. That's why I went, and frankly I talked about that, the educational narrative. But the point is that the NSF built that program, and it was really the first program that was focused on science from CubeSat, and basically repeatable, and basically put out an AO on a regular basis. Per AO, even today, they get more than 25 proposals and select 1 to 2 proposals. So it's a highly successful program, and that went up. Shortly thereafter, 2 years or so thereafter, NASA, which I was in some of these meetings at the Space Studies Board and so forth, which attacked NSF in some cases or marginalized NSF, basically started investing there too, and basically started investments both in centers and in competitive programs, and ramped it up. So you have educational programs, technology programs overlapping with this, mostly from the DoD, and then science programs. And so the NASA programs I'm going to show you are many, and depending on how you count, 10 to 15 or so NASA programs that in fact are funding CubeSats right now. But what happened in the last few years is that emergence of these 2 other colors, which are imaging and communication, which is in the commercial space. And in most cases, the large majority of these bars, of course, is one company called Planet Labs. I'm going to talk to you about it. But basically, this company is funded from the early pioneers there at Ames and in universities that really kicked out these initial CubeSats. These companies are now a large fraction of the CubeSats launched today. So you have different phases, educational phase, technology phase, a science phase, and a commercial phase that are starting. All of them are relevant for the future of this technology. Every phase does not cease. It's just a ramp up. There's still a lot of educational spacecraft out there. There's a lot of technology spacecraft out there, as you see, but there's an emergence of new. A few words about the NSF programs. The objectives of that program was to perform new science measurements, but also couple that with education and training of the next generation STEM workforce. The only other point I want to make is that this NSF program can only work in collaboration with Wallops. NASA was always early on a partner for NSF to really help enable that. The role of the NSF CubeSats really should not be understated. In many ways, they're pioneering because of the fact that they're the first systematic support of CubeSats for science. Created educational opportunities, but also innovated in many different ways. And I think the one thing I want to mention is the creative management techniques, which we would refer to in the report as fly, learn, refly paradigm. And so basically the way I would describe it is with this RAX spacecraft, PI sitting right here. RAX was really a pioneering spacecraft. It clearly had important science measurements that were done. It was really one of the early ones. And so basically when Jamie launched RAX, for which he spent close to 90% of the budget initially, when, according to the NSF program director, RAX worked, kind of showed that the measurement makes sense, but basically there was a degradation of one of the subsystems, which happens in space technology, right? And so basically what Therese did is she funded a second building for close to 10% of the money, a little bit more, but close to 10%. Launched a second one, which did all the measurements that now are in the published literature. And so basically, so that kind of fly, learn, refly paradigm is something that is really creative. The Air Force is using it too, but it really is unique to CubeSats. There's never been a spacecraft where you did that otherwise, just because it's too expensive to refly a spacecraft. And so basically, the creation of the commercial sector, in some cases, can be traced to the experience here also, because it created a repeatable market. And people wanted to see that. I want to quickly talk about the education and training program. For this, I used the example of the Air Force's NanoSat program. We have other data in the report for the NSF. But the point is that currently in the US, more than 1,000 students per year graduate with educational experience in CubeSats. And the distribution here, this is by universities that have provided their information. You basically see the diversity of engagement. This is from 10 universities. You see that the engagements of undergrads to grads is roughly 10 to 1. So there's a lot of undergrads that are getting engaged there, undergrad aerospace engineers, many of them, or electrical or mechanical engineers. But the graduate students are really becoming a substantial fraction of this, including at the PhD level, in which they provide PhDs. I know Jamie has advised some of these PhDs. There's also masters who do that, and then basically what you see is that there's output from this, which are journal publications, but also conference papers and presentations and so forth. So again, keep in mind, there's an undergrad component to the education, and there's a grad component. The grad component is much more similar to what you would consider in a rocket program, in which you basically launch a rocket to explore the ionosphere or something like that, in which a grad student really gets her PhD from that work. So this is some words about the education, and we think it's really important. The education remains super important, not just for a university, but also for other players in aerospace engineering. I want to talk about the NASA programs. You're not supposed to read all of this, but basically recognize that at the bottom, you have the National Science Foundation with the spacecraft that have already flown, the ones that are planned, and kind of the time frame over which. You see kind of in the National Science Foundation, it's kind of the same amount of spacecraft have flown that are planned. So this is a program that's up and running. Every other program, and there's, you can go look at them. Some of them are inside center, some of them competitive. There's a heck of a lot more in the second column than in the first one, which tells you that many of these programs are just ramping up. So in other words, in many of the programs, nothing has flown. Look at Astrophysics. Some of them are just ramping up and are basically moving towards kind of more repeatable and large programming. There's a lot of them, and frankly, we heard a lot of feedback that it's hard for people who are not part of the community to understand what's happening within NASA, just because there's so many of the programs. A few words about international participation. At this point, by launch, but also by activity, US is the key player. It's at the 75th percentile or so. You have other countries, though, that are making substantial investments, such as Japan, Denmark, Germany, and so forth. And many other countries. Many countries only having one spacecraft, like Switzerland, Israel so far, but are really investing more in it. We were really impressed by some of the international efforts and what they did, how systematic. They're supporting very often, led by a few universities in collaboration with government agencies and really being systematic about it. In Germany, I would say, picking up the key research topic that has caused a large fraction of these spacecraft to be developed is focused on constellation design. In Denmark, there's some really exciting missions focused on migrating birds over oceans, for example. You know, kind of really interesting things that you wouldn't have guessed are in space missions right now, you know, and so forth. So there's a variety of programs, and many more countries are coming on board. This is just the countries by launch in the last few years, and you basically see a different set of colors popping up. Different set of countries, all the way from Singapore to you know, Japan and Italy and so forth. One of the key questions that we're always asked was about the success rate of CubeSats, and so we spend a whole part of the report, which by the way is openly available and you should read in more detail than I can give here, where it seems that I'm contradicting the report. The report is right. The report is what is signed off, not what I'm saying here. But the success rate of CubeSats is summarized here, and you see three colors. The first one is in red, and that is the number of CubeSats lost by launch failure. You see kind of some smattering of red ahead, and then a heck of a lot of red in the last couple of years. And the reason for the lot of red in the last couple of years is part of it is just bad luck. You know, Falcon 9 was not supposed to blow up. Neither was the orbital ATK vehicle. One of the vehicles that blew up is an experimental vehicle, so CubeSats take risks. The other reason this bar is so high, so large, is actually each one of these launch vehicles had a lot of CubeSats on board. And so basically what happens is when you only have one CubeSat on board, you get that little tag. You know, if you get 20 CubeSats on board, there's a lot of red on this chart. So what you see is a real change in how CubeSats are being launched. So now many of these launch vehicles have many CubeSats on board. That's issue one. So launch is an important failure mode, but it's not a failure mode we basically has anything to do with the vehicle itself. And so that's why what we really want to look at is CubeSats deployed, not CubeSats put in the launch vehicle as a metric, you know, the ratio of CubeSats deployed. So what we did is we looked at in all public literature, we actually called up PIs where it wasn't clear and basically asked about mission objectives and to what extent a CubeSat was achieving mission objectives. Now, if I'm an educator and I launch a CubeSat, if the CubeSat says bleep, and it really wasn't a harder mission objective other than the education, that's fine, right? I mean, it does the job. It's like I have, you know, the team didn't kill each other, you know, like I got the learning that it takes, the humility from touching hardware, you know, that comes from that. You can't learn any other way. Kind of, it's actually harder than it looks, even if it has heritage, you know. So it's all these learnings. That's what that is. On the other hand, a science mission objective have nothing to do with that first bleep. It has nothing to do with I could, you know, in fact, do a handshake with the communication. It's all about science data. The only thing I care about as a mission objective is science. You see, so kind of the mission objectives matter in here, and you can either fully fulfill mission objectives or partly fulfill. So if you look at this, so far, until the end of last year, 33% of CubeSats deployed have fulfilled fully the mission objective goals. 67% have partly fulfilled goals. So you basically say, wow, that's not a very large number. When you look under the hood, though, you realize that in the first 7 years, fully and partly fulfilled objectives are at 35%. In the next 7 years, they're at 71%. So the community is becoming more successful in these launches. The one thing that stood out to us, though, as of end of last year, is the NSF CubeSats, including this learn, reflight, kind of as investigations, have fulfilled to 92% fully or partly the mission objectives. That, we think, is a really good number and is hard to beat, frankly. So why is that? We analyzed that in the report, and it really is because of at least two reasons. First of all, the mission objectives are aligned with our natural feeling for what success is, which is data. Any normal space mission, data is why we build it. It's not, any other reason, not to prove technology primarily. It's to get data. So it's aligned. The second one is that these spacecraft are funded at the $1 million level, 0th order, not at 10K, like some of the others. And so it takes some money to actually be successful. The third reason, I'm going to add a third reason, is, and there's an analysis that the Aerospace Corporation did that basically showed that the more experienced the team is, the more successful they'll be. So in general, the NSF spacecraft have been launched by more experienced teams as opposed to some of the other programs. So here's your success rates. All right, so these are the data. So I want to talk and kind of tell you how we analyzed that data and how we looked at the future. And really, when we looked at these data, it seemed to us that they looked like the beginning of a disruptive innovation. So I want to quickly explain what that is, then explain to you why we said that, and then kind of move on, because I think kind of a lot of the guidance that we gave to the agencies relates to that point. So let's talk about innovation. In most cases, innovation relates to better is better. An innovative car is a better car, a faster car, a car that does something the other car doesn't do. So you add. It's not a cheaper car typically. It's a better car. Okay? And so that's how we buy things. Kind of more innovative is more expensive, is better, have more performance. There's one really counterintuitive way of innovating in which worse is better. Worse is better. And that is this disruptive innovation. And kind of the way I would explain it to you is with the example of my first laptop. And yes, I'm that old, right? So the first laptops came out, and I wanted to get a laptop. Why? Because I wanted to go skiing while I write my PhD thesis, right? So I needed to move the machine. So I bought this laptop. First of all, it was crappy. Compared to the desktop I had, it was cheaper than the desktop. That was the only advantage. But it was really slow. And frankly, after a few months, it burned up. Because you remember how hard it was to make the laptops work with the thermal design. And so basically, I went right back and bought a second one. The second one was already a lot better. And frankly, I almost only use laptops now. If it wasn't for confidentiality, I only would use laptops now. But that's what it is. OK, so basically, it's a process or a product or a service takes root initially in a simple application at the bottom of a market and relentlessly moves up the market. That's what Christensen defines it. And so it's really in an economic shift described, an innovative shift that's really highly targeted towards an application and user that's otherwise underserved. So that's how disruptive innovation happens. The end state, and especially the level of disruption, is unclear at the beginning. I'll give you an example. The cameras here. So basically, if you look at these cameras, first of all, there's many more pictures taken than 10 years ago. Many more, 10x or more. They basically wiped out the small camera market by 80%. The small camera market, the ones that we used to bring to vacations, they're gone. There's only a few left. The high-end camera market, that some of you take pictures on, really beautiful pictures, has only been affected by 5%. And frankly, there's indications that it's going to go up more. So in other words, disruption doesn't mean that the whole market disappears. It means that a certain segment gets touched by this disruptive force. Because all of a sudden, the kind of cheaper approach is as it gets better, kind of wipes out what was there before. OK, so why? What are the kind of, in the literature, what are the kind of characteristics? So the performance is at the start poorer than the status quo. It's significantly cheaper than the status quo. The users, there's a user group that is generally underserved. It's kind of a group that did not kind of get served by the regular technology. The speed of improved performance is really rapid. So it improves really rapidly. And then the origin so often is on the outside of the mainstream and has an enabling technology, typically at the heart of it, that rapidly, sometimes often it's tied to Moore's law somehow, whatever does that disrupting, right? That's why the laptops are so powerful today. And it has development models that are really different than some of the others. So how are CubeSats disruptive technologies? It's kind of obvious from what I said already, right? But I'm just going to pick out a few, namely that really the users initially were from outside of aerospace engineering. So it's not surprising that a given NASA center, let's say at Goddard, did not come up with CubeSats. Not surprising at all, in a kind of with your hat on as a disruptive innovator. It's also clear that the speed of performance is really increasing dramatically, and I'm going to show you some of these charts. And the development models are really different. I mean, the large majority of commercial players in CubeSats are entrepreneurs that are really looking, are either data companies or they are component companies. And they're really different than generally now, a traditional aerospace company. So once you get that, you basically recognize, of course, it's unclear how much CubeSats will do, but you basically recognize, well, this really looks like the beginning of such a wave. So what is unique? See, my laptop that I bought was useful because it allowed me to carry it to the ski resort, right? I don't know why you bought a first laptop, but something like this, you wanted to carry it. What is the CubeSat useful for? The reason it's really important to ask that question is, yes, use the right tool for the right action, right? Yes, you can nail down nails with scissors. It's not very effective, though. Like at the end, you still want a hammer, right? But what are the things that scissor does? It cuts. Hammers don't do that well, right? So what is the CubeSat able to do that kind of traditional spacecraft really can't do so well? So first of all, they are rather standardized and therefore have and are creating a supply chain. They are parts that are being bought now that are available that were not there before. They are cheaper. So that basically allows to conduct higher risk activities and also that fly, learn, refly paradigm that we already talked about. It enables new mission types, especially high-risk orbits. I'm going to tell you what I mean with that in science. And also secondary lines of sights, as well as targeted science, kind of science in which you address one question with one instrument in a small spacecraft and are done with it. That's really not, you can't do that any other way. But I think the one thing that we spend a lot of time on is really the creation of entirely new architectures, especially constellations and swarms, of many spacecraft. So those are the things we think are differentiating. My third point is about publications. I'm not going to talk to you a lot about this. You see that publications, of course, are going rapidly up. Close to 75% of publications to date are in engineering journals, not surprisingly, because a lot of this is really developing the technology infrastructure for that, the capability. What we did, by the way, is we read every single published paper in science and read it multiple times and scored it according to certain innovation matrices. I kind of really scored it directly and basically from that conclude without any caveats that CubeSats have already produced high-value science and demonstrated by peer-reviewed publications in high-impact journals. So not going to talk, there's more in the report. Go read it if you're interested. So I'm going to tell you some, remember these sample missions. I already told you where I'm going with it, but these are these sample missions, and this one is one that's built by the University of Colorado. And I kind of talk about it as kind of a mission in a high-risk orbit. It's, of course, radiation belt mission that basically is measuring electrons at high energies from really low altitude. Why is that important? Well, The Van Allen probes are high up and measuring to an unprecedented fashion the evolution, temporal evolution, and the energization and the emptying of these radiation belts through processes that are being studied by you, Mike, and others. At the bottom, at the Earth, through balloons and other investigations, we see some of these energization events that are down there, and we kind of see that there's dissipation of energy from these radiation belts. But in many cases, some of these events on the Van Allen probes and the events at low Earth, near Earth, are really tough to connect. And it's that kind of mission that can do that, flying really low over the Earth atmosphere. And that's what they did. In fact, one of these papers is in Nature that, in fact, did this connection to a way that really made it uniquely a unique proof of a given hypothesis that is there. So this is what we would consider kind of a high-risk orbit, often with other missions. It's almost never a standalone thing. It can be, but it's often with other missions, a secondary line of sight. Without the Van Allen probes, you would not have made a Nature paper with that journal, with that data. Chris is here. We spent a lot of time on Cygnus. And first I want to tell you that Cygnus is not a CubeSat. If you don't know, you just go down the hallway and look in that door. And you see the posters. Cygnus is a bigger spacecraft than a CubeSat. Basically the reason we put it here is for two reasons. First of all, the PI, sitting in the room right now, told us at the committee that without kind of the CubeSat evolutionary process early on, it would be really hard for him to propose and successfully win Cygnus early on. There's parts available, there are things available that Cygnus is using. Not all of them panned out. Some of them you had to develop independently. That's the first one. The second one is because it really shows how a distributed system, a swarm in this case, so it's not a constellation that's maintained at the given geometry, how a swarm can do science that otherwise a single spacecraft not only cannot do as well, but can absolutely not do at all. And so, of course, what I'm talking about is the measurement of winds over the ocean surface, which is an important predictor of the importance of a given cyclone as it makes landfall in its evolution. And so if you want to do that, there's before Cygnus, there's basically two opportunities for you. There may be more, but the two that I'm aware of is the first one is you sit on a plane and go into the cyclone, measure some stuff. Heard it's bumpy. You don't want to do that too often. You can't do it on a regular basis, but that's one opportunity. The other one is you fly over the cyclone with a radar, and you basically shine a radar down. Takes power, right? But you shine a radar down and you look at the backscattered light. If you're shining off a surface of a mirror, or a flat surface of water, what comes back is rather coherent, kind of a backscattered light. You know how to interpret that once you know some scattering theory. If there's, of course, a wavy surface, this thing comes back increasingly incoherent and distributed in a spatial dimension from what you have shine, what you shine down. And so basically, what this does is, to a certain extent, complementary measurement, but a similar type of measurement using GPS signals that are, of course, also, because they're electromagnetic radiation, reflecting off the surface of water. And they're coming back, and the same kind of coherence measurements are being made. Now, what's interesting in this is that because of the fact, largely speaking, a radar to zeroth order is $1 billion, zeroth order measurement. This mission includes 8 spacecraft and is being developed for $200 million. And so basically, what is possible because of that is not only a comparable set of measurements. Nobody says they're identical, but a comparable set of measurements that give very similar type of outcomes. But it is able, you can, because of the innovative orbit technology that's being deployed here, you can do this not with repeat times of hours and days, which is what you would get with a single spacecraft, but with repeat times of tens of minutes, 20 minutes, and so forth. That turns out to be the important timescale of evolutionary change for this kind of weather system. So you see, kind of by breaking up a big space mission, a single big space mission, into many small ones, enables science that otherwise you can't do. That's the key point that I want to make here. Space weather is a similar type of problem. This is a chart that Dan Welling gave me here. Basically talks about the complexity of space weather. You're not supposed to read all of these boxes. Just recognize that kind of on the left of here are boxes that relate to the sun that have some measurements wherever there's orange arrows. And you see there's a lot less orange than you'd like. And then you have one orange arrow at L1, where we have a spacecraft called ACE and Discover here that we're running instruments off here at the University of Michigan. And then you have, of course, the magnetospheric type of data. And the models that are being developed are really starved by data. You know, you have basically the equivalent is to do a hurricane prediction with 2 weather stations or 3 weather stations. That's kind of what we're currently doing in space weather. We're really good at some of these models. In fact, award-winning in this particular one, but we lack data. How about if you could instrument space? For example, the magnetosphere, the upper atmosphere, even if you could instrument the inner heliosphere and really make these data more dense, they could help you understand, drive the models better through assimilation, but also help you understand science that currently really do not get revealed because of the fact that these data are not available. So what I'm going to do now is, so this is kind of the constellation piece. So there's a lot of excitement about constellations in Earth science, lots of excitement in solar and space physics, or heliophysics as the NASA people call it. This is an example of targeted science, one instrument, one question. This is by Arizona State together with JPL, looking at the hydrogen content of the polar regions of the moon, one instrument, one question. This is the kind of thing you could not really get a $100 million spacecraft, or going to the moon is probably even more expensive. But you can do it with something like, in this case, a $10 million or so project. This is not 100K. Okay. There's a lot of data out there now. You see it, commercial data. I just want to show that. This, of course, is the Ohio River flooding in Illinois. This is on January 3rd. This is shortly thereafter. So these kind of data are now basically once per day. We have these kind of data are coming down, are being distributed in a commercial market, and are really becoming interesting for science. Not because they do everything that high-resolution spacecraft do, because they do something better, which is high repeat times. So kind of things that require these repeat times are there. So I'm close to the end, but basically I want to talk about this high-value science. I already said that it produced high-value science as demonstrated by peer-reviewed publications and addressed decadal survey science goals. But CubeSats are useful as instruments of targeted investigations to augment the capabilities of large missions and ground-based facilities. They are enabling new kinds of measurements, and they have the potential to mitigate gaps in measurements where continuity is critical. There is a caveat already mentioned, which is that CubeSats cannot and should not really address all science objectives and are not a low-cost substitute for all platforms. Certainly not today, and not in the foreseeable future. All right, so you could ask, what are the technologies that most hold back the use of CubeSats? And so what we did is, as we went through each one of these communities and the missions, we basically looked at the technologies that are throttling the progress. And here's what we found. We can talk about this like solar and space physics, earth science, and so forth. But really what I want to show you is kind of that in these missions, a bunch of words kept popping up over and over again. The first one is communications. Right now, for a large fraction of these missions, only 5 to 10% of the data get played down. There's just not enough bandwidth. It's complicated to get these licenses. So it's kind of a complicated thing because it's part policy, part science. But communications is really an issue that throttles the progress we can make with CubeSats. Propulsion is another one. Propulsion is not always have the same function. Sometimes propulsion is just to make a mission longer. Sometimes propulsion is used to set up a constellation, and sometimes propulsion is used to go somewhere. And so basically, the propulsion will not likely have a single kind of solution. There's a multitude of solutions that need to be developed to basically make this work. Sub-arc-second attitude control is another one that relates to many imaging applications, such as astrophysics or the solar type of applications. I'm going to talk to you about kind of the progress that has been made, but that's something that pops up too, as well as miniaturized sensors for both imagers and kind of in situ sensors. Many of the sensors just really aren't there yet. And so kind of the quality of the sensor limits what can be done. So there's, of course, a recommendation that went to NASA in a report that basically said, here are the focus areas in response to the charge. There is, however, rapid development that has already happened. This is from another study that we're citing in there that really shows that, and frankly, there's a really extended chapter that we try to show where CubeSat started, where we are right now, or what's emerging, and where it's developing in a few years. And you really see that all of these things, including attitude control, propulsion, and radiation tolerance, which matters in some of these applications, in fact, have made a lot of progress. And not only are they being developed in NASA centers, for example, there's commercial piece parts that are available in some of these cases that can be used. Just to give an example of one of them, this is the speed of development in attitude control. By the way, if I put a new symbol here, it would already be further down from just last month. But during the last something like 10 years, the attitude control has gone from about 10 degrees to something that is proven or being flown at 0.1 degrees or so. Where we really want to go, if you look at this in arc seconds, we're at getting to like 30 arc seconds. We want to go another 2 orders of magnitude. We may not get the whole way, I don't know, but the point is the development has been rapid already. I already made the point that propulsion will require a multifaceted approach, so I won't repeat that. But I just really want to repeat that building constellations and swarms is more than just building more than one spacecraft. And so actually we made a recommendation that there should be a tremendous focus on constellations and swarms. Constellations and swarms of 10 to 100 spacecraft requires the kind of problems that I think you're addressing, Jamie. Like, if you have 100 spacecraft in orbit, how do you run your ground system? So at the end, you get the maximum amount of data done. This is not a trivial solution at all. How do you manufacture these 100 spacecraft? How do you test them? Chris, I was lucky to sit next to Chris on a plane, and he told me about kind of lessons that he learned and that the team learned that's sitting here doing this. This is a non-trivial thing. Learning how to do constellation is something I think that's really important, and in fact, is the enabler for many of these big missions that I think have the most promise to do breakthrough science. So there's risk strategies is another one. You talked about testing, but also just where and how you test. How can you afford to test this thing? So basically, just a couple more minutes on policy before I close the talk. Basically, when we looked at policies, we really did so because we worried that policy issues could be have a throttling effect on the evolution of CubeSats, just the way technologies do. So in other words, if policy issues are not moving, all of a sudden we cannot get to the level that CubeSats can go to do high priority science. And so basically what we looked at is really 3 policies: orbital debris, communications, and launch vehicles. I'm going to talk to you about launch vehicles first. Launch vehicles, the situation is that the availability of launch opportunities is not as good as it should be. Right now, there's close to 50 CubeSats waiting for launch. So we're already behind. By the way, the answer should not be 0. We don't want to size the opportunities of launch vehicles to 0. That means that we have too much. So I'm not trying to make that point. I'm just trying to make the point that it's going to get worse. And so basically, focusing on the availability of launch vehicles, especially also for planetary type of opportunities, is really critical to learn for the community to learn how to use these assets. Communications is something I'm not going to talk a lot about in this talk, but there's a lot report, and that is that communications, in many cases, remains challenging because the time scale of getting your communications issues resolved on a policy side, kind of the kind of permit side, is almost the same as the development of the CubeSat. And so kind of if you're a commercial player which has a lot of money, you can solve these kind of problems. If you're a university group, kind of the administrative overhead for many groups is perceived as being inordinate. I mean, so that's what communications is about, and we're running out of spectrum. So the issue on communications really is both a technology issue and a policy issue. And so there's some ideas, of course, we had and we talked about, and some of them are there, but to solve it requires both. Let's talk about orbital debris. There's a lot of being said about orbital debris, and kind of the point of this chart is here's the orbital debris, and in the last few years, and you know how it has gone up, and kind of the point I'm making here is orbital debris is a big space problem, not a small space problem at this point. And basically, the operational spacecraft down there, close to 100 or so, are CubeSats of the order 0.5% of all bodies flying and being tracked are from CubeSats. The vast majority of these parts are, you know, pieces of spacecrafts that happen because of the Chinese blowing something out of the sky, or we're blowing something out of the sky, or because of spacecraft bumping into each other. At the end, mass is what matters here. These things will fragment, so there's just more mass in big spacecraft. However, the number is going up, and you know, so it was kind of the close approaches involving CubeSats is crossing kind of 5% or so. The reason for that, by the way, is simple. Many of these CubeSats are deployed from the space station, so if you go down with the space station, you know, they come around. You know, so kind of a number of these are really close approaches from the space stations, and so it's not too surprising. We do feel, however, that there's real challenges. In fact, many of the kind of, especially deployments of many spacecraft, are actually really hard on the current technology. This is data that was given to us by JSPOC, you know, where they basically talk about how difficult it is to patch together orbits that they're tracking, so you know which body is which when you see it on pass 1 and pass 2. And kind of doing that the right way is really hard. There are ways that the companies and the providers can help by batching or by providing information. For example, Planet Labs is a lot faster figuring out where each one of their objects is than JSPOC is. And so basically they can help providing that. We think there's tremendous opportunities of the community really helping. There's also some policies we might consider. Again, we did not recommend that, but one of the things we talked about is the fact that many of, like a technology development CubeSat, requires 2-3 months of operation. How about if the orbit regulation for that particular CubeSat is not 25 years, but is like 5x, like 5 times the nominal lifetime, or 3 times the nominal lifetime. So it's down in a year, as opposed to in 25 years. There's no reason for something to be up 25 years. It's supposed to operate for 2 months. Is the point that we're making. In many cases, of course, you want to be up for that time, but you know, the policy probably needs to shift in some of these cases. That's what we talked about in orbital debris. I already gave you the bottom line up front, and that's where I want to stop. Kind of the point is the committee really saw tremendous opportunity in CubeSats, even though we may have not stumbled onto it early on. The reason we see that is because we look at the data, the evolutionary trajectory of where it came from and where it can be. We think that there's unique opportunities for these platforms to solve some important science questions, address some important science questions. Not all of them, but some of them for which I think this group cares a lot about. What I want to do is pull up the URL that tells you where you can download the report if you want to learn more. I thank you, and happy to answer any questions first about the report and then engage in a discussion. Thank you so much.
We have such a violent launch on top of millions of pounds of thrust. Ridiculous vibrations. So we actually have a vibration table in the Space Physics Research Laboratory that allows us to shake the satellite at very high rates.